Okay, so hello everyone. Only Prashant is here. I don't see anyone. That's why I was waiting that maybe some other person, other participants join. But let us start with today's discussion session. So today is the week 3 of this NPTEL course named as Coherence and Quantum Entanglement. So in previous class I would like to say that in the first half during 5 to 5:20 p.m. that I had some glitch and I was badly I needed to I had some work also, and due to that reason it became delayed to start. It will not happen from the next from today and so on, from next and the other next classes. But all right, so I could not stop that. So okay, so I hope that for that reason I think many of you have joined earlier and then somehow you guys gone, because you guys thought that maybe that this class will not gonna happen, but it happened, but after some time actually. It started at 5:20 p.m. So if you have missed that, please visit to the YouTube channel, and you will be able to get the recorded lecture. And if you have any doubt, then you can ask me through my mail, through ask a question portal or YouTube comment section. And everything will and it was delayed for uploading the things in Google Drive also in the past week, due to very hectic schedule. So I have already uploaded, and from now on it will be very streamlined. It will be in very streamlined manner, like everything is going to upload after just half of an hour or 1 hour, or by tonight at least it will be done. So that's from my side before starting today's class formally. So as I tell you every time that that welcome to this today's discussion session, which is week 3, and from today onwards we'll have much more interesting thing. First 2 week classes were like very not so much involving or not so much enthusiastic, or uh, I did not saw any interesting thing apart from problem solving or telling something, because that was just a warm up classes, as well as to make you habituate for this course. That's why. But now onwards, I hope whoever is taking this course seriously and going to appear for examination, all of them have already started watching the videos, as well as the problem solution, quiz, assignments, all those things. And now onwards, our main motivation will be to discuss the questions, various types of questions. Solve this. I'll solve those very in by doing each and every step, as well as because this discussion's main importance is there, that such that you guys can code much better in your examination and assignments. I Such that I can help you to solve those questions. And I have already received about 3 or 4 mails and LinkedIn messages also, that people are facing problems in solving this assignment question for this course. And so for that reason I will again and again tell that if anybody has any problem you want to discuss, please let us know. We will help you and follow this week lectures as well as these discussion sessions, because to solve the assignments most important is these discussion sessions. Then you will be able to solve the questions, and maybe somewhere at some point of time direct you can get some direct solution of any assignment questions also. So take these discussion sessions, any of these two discussion sessions are there, one by Radhika and one by me. Anyone is okay with any one of you, whoever is comfortable with whichever time, just join that. You will be able to solve much better for the assignment. You will be able to do much better in the assignments. And if before starting today's class, so let me.
Nilasika,
Yes.
one thing I want to ask you, one class is also today is, I think, 3 to 5 o'clock.
Yes.
This is online classes, and I trying to do it, but unable to log in.
Okay.
Or this is a recorded session, previous recorded session.
Not previous recorded session, it should be a online live class, but I don't know what happened today, but it should be exactly what is here for now, exactly same. And questions and the things may be different. Maybe I can solve that question in the first class, he can solve the question in second class, that can happen. But both of them are same and you can join any one of them.
Kindly to confirm it. I try to do sometimes,
Okay,
but
I'll
unable
confirm
to
it with
log in a
Radhika.
class. Okay.
I'll
Okay.
confirm.
Thank you.
Okay, yes. So before going, as I know Prasant, you all already know about these things, but still, for formality, and I need to upload these things, so I tell these at the starting of every classes. So this is the drive folder link, which you can from where you can find anything that I am discussing here, as well as maybe I can give some more things time by time. Today I have uploaded one photo, maybe you can check. That is a setup of doing just what we do in case of single photon single interference with double slit and single photon also. So today my plan also is to show you, I mean, obviously I am not going to perform any experiment now, it is not possible as this is online, but I have recorded one experimental session just to show you that how this because people has lots of confusion and questions regarding the Maxander. It is not a Maxander, we are doing it with SLM. I'll tell about that also, what we are actually doing in that experimental setup, and how to do the double slit experiment, as well as how to do the double slit experiment with the single photon and what we actually observe. I think this will be very interesting to even feel that what exactly is happening. Maybe then some of the questions that many of you have, uh, you guys can answer it by yourself. And one more thing is to I want to give you the YouTube channel link also. Alright, so this is the YouTube. I don't know why is this happening. 1 minute. One minute. Mm-hmm. Okay, all right. So I hope you guys can, if you search in YouTube by my name, then you can also find it, or just go to this link, and you guys already have, I think, the link of video recording and drive folder link, all of those in your SWAM portal through NPTEL SWAM portal. There you can find week 1, week 2, week 3, week 4, and after that there is a bar which is written as problem solving sessions. There you can get the Excel sheet for all the recorded discussion sessions. All right. So. So this is the third class, and I am Nilakshi, and today we are going to mainly discuss about the first maybe 30 minutes or 20 minutes, maybe 20 minutes. We'll discuss about the single photon interference, single photon interference, as well as double slit experiment, and what are the experimental setup that we have performed. Those things I want to show. And before going that, I want to tell that for week 3 the contents of lectures were second order spatial coherence theory, some essential mathematical concepts for doing the second order spatial coherence theory, as well as quantifying the spatial correlation, then Wolf equation, Van-Cittert-Zernike theorem. all of them are well described, very well described by our professor. But in the first two classes I was going through the theory part again, just to make you habituate with the things. But I think if you are getting the temporal coherence theory, then you can also get the second order spatial coherence theory, second order angular coherence theory, and second order the polarization theory of coherence for the polarization basis also. So one by one we'll go through all of this, but if you understand one, try to understand one, then you will be able to get the other one also. And I have already mentioned all of these things, that why coherence is so important here, and why we want to understand coherence first to understand the quantum entanglement in the after understanding this coherence. So I am not going through all of this, and from now on mostly I will discuss the theory part. You guys, if you want to ask anything about theory, you can ask me, but I will not go through all of the theoretical calculations thoroughly, because those things are already done in the lectures itself. Okay, but to give you just before going, this is a setup, like whatever I was saying, that we this is an experimental setup when we are performing this double slit experiment for in highlight level as well as single photon level. I will describe this, but before going to that, let me just give you a glance that what was these things in your lectures for week 3. Here you learned about second order coherence theory in spatial degree of freedom, that means position momentum degree of freedom. And we are looking here for a spatial coherence effects at a particular frequency, which is omega. To keep it simple, we consider this actually it is happening in a particular frequency. That means it is a monochromatic source of light is coming. If you are considering something else, then you can omega 1, omega 2, whatever that, for each and everything you need to consider this coherence effect. So but for understanding, we don't need to go through all of this, and mostly when I working, we work with laser light in case of photon, and of course you can work with led and so on, but most of them are in a particular frequency. If it is red, then it is 633. It is if it is some uv, then maybe 405, 355 nanometer, etc. So for understanding this spatial degree of freedom, coherence theory and spatial degree of freedom, we represent the time domain electric field vrt as a function of r and t, and we write it in the terms of Fourier integral. And then we saw that we can, if rho is equal to like rho 1 means equal to x1 y1, rho 2 means x2 y2, then you can write the similar thing similar thing like temporal degree of freedom. So maybe I can go to the this figure where we described here you see that you at r1 and r2 we have two slits in but this is now in position basis, and this rho 1 is nothing but x1 y1, and this is z, and rho 2 is x2 y2, and this is z, and it is passing through this, and this is just the two Young's double slit experiment. And then you can write u rho z equal to k1 u rho 1 0 e to the power minus I omega t1 plus k2 u rho 2 0 e to the power minus I omega t2. This was their detailed description was there in the lectures, and for the temporal I have explicitly done this in discussion session also, so I am not doing these things again. But to solve your problems, it will be very beginning level. It will always start from this beginning level only. So you need to focus on these things. And of course, always we need to keep remember of these things of the some of those essential mathematical concepts which you require to consider for a practical case also, which are stationarity in spatial degree of freedom, angular spectrum representation of space domain field, as well as those ergodicity and space average, and these four things mainly. So these were described in the lectures, so I'll not do those by writing the equations explicitly. And remember, there was one thing here, that was angular spectrum representation of a space domain field, where you saw that you have the u rho z. You can do the Fourier transform, you get the qx qy z, where q means here is the qx qy means here the transverse momentum. Okay. And of course, you can write that in terms of in wave equation, in position basis, and in momentum basis. You can, I mean, in simultaneous momentum basis, that is k square, it becomes, then you can write it in terms of Helmholtz equation. So if you solve the Helmholtz equation, you will get two solution, where you can get the propagating solution or evanescent solution. We are always considering for propagating solution, and then you reach to a function, I mean a relation, which are again Fourier, which is called the angular spectrum representation. And the uxy and a qx qy are related with the Fourier transform relation. So all of these things were done in your lecture. And after that, you gone through the space average, ergodicity, as well as how to quantify the spatial correlation, and how to find the visibility, and how the visibility is directly depending upon the spatial correlation, spatial cross correlation function, or spatial degree of coherence in spatial degree of freedom. So those things we have all seen, and we have also seen that for no correlation between different spatial frequency components, they are what kind of solution we get for the spectral S cross spectral density S rho, and for perfect correlation and for partial correlation, what we get. And there are many interesting things, by the way, for this partial correlation field. And those are actually the current research, those are actually related to the current research also. So after that, maybe I will go through once, because sometime there are some questions which are there in assignments, which you can see that some particular condition is given for the correlation. Maybe it is no correlation, or perfect correlation, or partial coherence, or partial correlation. Then what will be the solution? So those kind of problems also we'll solve. And then we learned about propagation of correlation, and Wolf equation came into the picture, and then we solve it, and we learn how the propagation of how the correlation function propagates, and we learned about the Van-Cittert-Zernike theorem. This is a very interesting theorem. Maybe I can discuss today that what you understand about the Van-Cittert-Zernike theorem, what you felt it, because this is a very weird thing. When I learned about this course and this Van-Cittert-Zernike theorem, actually this is showing in this picture, and this picture was also shown in your class, that class means lecture. Then you get to know about the Van-Cittert-Zernike theorem, and this is actually very important, not only from this quantum optics, or propagation of any medium, even it is even in its in astronomy also. This Van-Cittert-Zernike theorem is actually used for radio astrophysics. So the thing is that I felt very weird to learn about this Van-Cittert-Zernike theorem. So that's why whenever I discuss anything about this course with anybody, so I like to learn that what he or she has visualized about this Van-Cittert-Zernike theorem. So all right, so we'll solve the, and we have given some I have given one problem to you actually to solve for the to solve in homework, as a homework. And this was this problem, because the similar situation I solved in the previous class, and I gave this one to as a homework problem. Maybe this kind of field is also there in your home assignment. But nevertheless, so we'll also solve this problem today, that how to do this, because maybe I got some of the mail that you guys are unable to solve them. So, all right. Before going to the mathematics and all those part, let us get some essence of experiment today. So this is just a excuse me. So this is just ignore this week 2. This will actually be week 3. I'm sorry about that. And I think most of them are week 2 written. I have forgotten to change that. Pardon me, this will be week 3. All right, so this is the experimental setup. We guys were showing in a demo for the school students as well as college students as well as students at IIT Kanpur, BTech, MTech, and it was like a um, physics outreach event where we saw this experiment, and this picture is taken from that itself. So this is a laser. You can see the laser is coming, and we are passing it through some lens combination to such that because you always know whatever we are doing, it is very important to do proper lens combination to get whatever we are wanting at the source or object or the image plane or screen. Otherwise, if you are not in focal plane, then you will not get the Fourier transform. Or if you are in 4F imaging system, and if you are not in focal plane, then you will not be able to get the imaging. And I hope you guys are aware about 2F system, 4F system. But if anyone of you are not aware or want to discuss, or you want that I discuss all those things with you, then maybe then let me know. I will discuss them also. So so this is after passing through these lenses, it is falling on this SLM, which is a spatial light modulator. This is actually this is made up of some as you are understanding that spatial light modulator, which is there is some liquid crystal embedded, which is the SLM is made up of some liquid crystal corresponding. And suppose this is a plane, it is made up of liquid crystal, and with the liquid crystal it has each and every pixels like system, pixel correspond, and with each pixel it has some liquid crystal. Now if you give the particular voltage, then corresponding to that it will have some ramp, or it will like change its phase. It will give, like it was like previously this, and it will become like that or that, whatever phase you will give. You can give parabolic phase, which is actually for a lens itself. You can give you can give a linear phase, which is just like to add a etalon kind of thing. You can give any kind of phase. Even if you want to make your face as a phase, then also you can use that. I am not describing here the working of SLM, but this can work in that variety manner. There it can be amplitude only modulator, it can be phase only modulator, but now these are becoming complex modulator. That means we can do amplitude and phase at simultaneously with some method. Of course that is dependent upon basically simply with the Fourier transform method. So after falling on this SLM, through this SLM we are actually generating two slits. Slits means you can understand there are two slits where the light will pass and other things are blocked, and we are generating that. People sometimes use hologram. People can use two slits itself by making in a cardboard or whatever. But what we are doing in this thing is using SLM. After passing through it is again passing through the and we in case of SLM, we always collect actually the first order uh, mm, first order in light, whatever it is coming. Like when you will get the SLM pattern, you will be able to see that there are many patterns which are coming, because there is pixelation effect of this digital device, because of course as we are working it through some digital and controlling everything through computer, so and all those limitation will come into the consideration. And these are not actually limitation, these are actually the practical experiment where you need to consider many more things than whatever we think in theory. Just two slits and it is coming and providing interference pattern. For experiment we need such many things and need to consider all of those things to get a perfect pattern. So yes, after passing through all of this, again it is reflecting back with the mirror and coming to this EMCCD, which is called electron multiplied charge coupled detector, which itself it worth of 50 lakh itself, about I think 20 lakh to 50 lakh, exact price I forgot. So this whole setup is somewhat like 50 lakh setup, total setup. So after doing all of these things through this EMCCD, which can actually detect single photon level, the photons in a single photon manner, like a very less amount of light, very less, like single photon it can detect. So based with the help of this EMCCD, we are doing this double slit experiment, and you can see that this this is the GUI or the interface, computer interface. I have taken a screenshot of this.
Nilakshi, I
Yes,
have one questions.
yes, please.
Uh, uh, how to generate single photon? You have a laser source. There
Mm-hmm.
should be kind of some attenuator or some
Yes, there are attenuator. Yes,
density filter kind of
yes,
things.
there are ND filters here. Here there are
Okay.
ND filters, and even you can see this is in a room where we are performing with lot of light, but when the experiment will actually work, then this light should be off and all of those should be maintained. And of course there is ND filter also, and we are attenuating the light. And I think you also know that how it we are considering it is as single photon, because you also answered there, right? People were discussing in the ask a question thing, ask a question portal.
Okay.
Yes. I thought you answered, right? That
Yes,
thing.
yes,
Yes,
yes.
that was very nice. Yes.
Actually, that experiment you are representing a double slit experiment, no? Okay.
Okay, so yes, of course you are correct. Apart from lens, there are ND filters, of course, to attenuate the light. Without attenuation, we cannot do this. And of course, there are much more things, like we have control over gain of this EMCCD, where we can control the gain also, that after above a threshold it will collect the photon. Through that manner also we call it single photon, like both of the thing, one is the ND filter attenuation, and second thing is the gain of the device. So this is and of course you know that quantum mechanics is a detector dependent or measurement dependent experiment. All the experiments are measurement dependent. So by that manner we can say it as single photon level experiment, as well as the G2 correlation what you told, that is also true, and it provide us with the Poisson distribution also.
So for this experiment,
Hmm.
for single photon, how much typical power should be there for
Power
single photon?
power
Helium, neon
power of
laser,
the power of
single photon.
this helium neon whatever we are using, that is 5 milliwatt, okay. But
5 milliwatt after attenuation,
no,
right?
without attenuation.
Only after attenuation, it should be order of helium neon frequency. I think order of
H bar
if you
omega, like
yes, yes.
in its omega, like omega means
Okay, H.
633. Yes.
Okay, it should be order of around 70 dBm or 75 dBm.
Yes, something like that. If you calculate h bar 2 pi by lambda, where lambda is equal to 633 nanometer, then whatever you will get, it is up to that level. In
Okay,
some EV it will be.
okay.
Okay. So so this is the thing. And after that this is the double slit, and now if we do it with the uh, first let us take the take a look in the double slit experiment with the highlight level. This is not the single photon, of course. then you can see that you are getting a beautiful pattern. And whereas in the SLM, what we are talking here in this is the SLM device. And the in the SLM device, it is actually this there are the two slits, and there are several slit with these three in its digital units. Whatever here we can fix it like it is
And
three.
Lakshi, again, I
Yes,
have
yes,
one
please,
question.
please, please.
There is a dark also pattern is there. So there is a kind of a destructive interference or photon not falling, black screen, some white, black, white, black,
Where?
yellow, black, from
Here.
screen. Where some there is some also black is there between the two yellow pattern.
Okay, okay, here.
There is a yes, yes.
Okay,
So there is
those.
a black. There is a kind of a destructive interference.
No, this is not destructive interference. This is happening just due to the effect of loss. And like you can get sometimes Newton's rings due to, like, there are several optical instruments we are using, right? Using right, like the ND filters, then that lenses. If you simply use a lens and pass light through it and check the image, then you will be able to see this kind of pattern inside it. This is just the effect of dispersion, internal dispersion, and all those things.
Okay, and what about the between the two yellow line? There
Between
is
the,
a vertical black, yes, vertical black line.
this is the interference pattern, right? Right,
There
like
there is
whenever.
yeah,
Yes,
there is destructive interference for vertical black line.
these vertical black lines, the no,
Yes.
see, when you get the interference pattern, what is this? It is cos square, some cos square function, right? Cos square beta. And if you do the sin square cos square thing, right? So sin square means you will get an envelope, and in between that it will be a cos square thing. So cos square means there will be an see, this is the pattern, this is the graph that you are actually getting. And corresponding to what, this is the CCD plane what we are showing. And if you take a card, then what you will get is this. Pattern means what? Pattern means does not mean
There, actually, there is some sinusoidal is there. There is a kind of visibility is there.
mm-hmm,
है ना? Pattern visibility is. A peak where there is a peak, there is a kind of a constructive interference. There
and
is a
there is a
dip.
destructive
There is a
info.
yes,
Yes,
destructive
yes, yes.
interference. Okay. So this black line uh, coming due to a destructive interference. My question was that.
The thing yes, in that term you can say it. If it is a simple double slit experiment, this is constructive, this is destructive, yes. But actually, when you will see the interference through a Mach-Zehnder interferometer, this is not an interferometer setup, right? This is just a normal double slit experiment, and that's why you can say this is constructive, this is destructive, absolutely fine. But when here, no confusion. But if you are telling about pi phase or phase difference between two paths, then that we can see in the Mach-Zehnder interferometer setup, where you can be able to it will not, with just a single shot at particular phase, you will not be able to see the constructive and destructive. And for a particular phase, you cannot say that this fringe pattern is there, it is constructive, there it is destructive. No, not like that. But in case of here it is constructive, destructive. So why I do not want to comment in that manner, constructive, destructive, because of the because when you will see it with the Mach-Zehnder, na, then actually the the definition of constructive and destructive thing changes with its extra phase, which is called geometric phase, what we add there. So you cannot generalize, but for this system it is constructive, it is destructive. Are you happy with my answer, or did
Okay,
you
madam.
get why you wanted to mention?
Okay, okay. Go ahead, madam. No problem.
All right. So yes, after this double slit experiment, we want to show you single photon experiment. And before as Prashant, you told me, so I just want to let you know that I have shown all of this calculation, right? the two photon the second order coherence theory for the temporal thing, where I have shown you that there is if we do the interference, then what happens, there is something called cos terms comes, right? And for this cos square terms, what we get is the interference fringe. I maybe or may not be, I forgot that I have explicitly mentioned it or not. So that's why this fringe pattern comes. And but that was a Mach-Zehnder interferometer setup. That is there, the constructive and destructive means you need to add some path difference corresponding to 0 phase and pi phase, which will and if you subtract them out, then you will get the coherence function, and corresponding to 0 phase you will get constructive interference, corresponding to pi phase you will get destructive interference, not simultaneously, but both of them are function of cos. But here it is just a simple double slit experiment, what is Young's double slit experiment tells us. So here also we get to see the double slit interference pattern only, cos square theta. Here you can say in a single plot itself that constructive destructive, maybe you can explain it, but actually constructive and destructive comes in the interferometer due to different geometric phase we add. We will come, and so not today's class, maybe in maybe in next class I will give you exact I will show you the setup for Mach-Zehnder interferometer and Mach-Zehnder interferometer, and corresponding to that the result also I will show you, that if we give this, then this is called the constructive, this is called the destructive, and if you subtract them out, then we'll get the coherence function. So maybe then I will again come back to this double slit experiment, where you can, by comparing both of them, you can understand that why I am not telling it as constructive destructive particularly here. Alright, so so maybe showing in terms of Mach-Zehnder interferometer will clear this thing. And the second thing is that this second single photon experiment that I want to show today, I have the video graph also. So this is a this is an in between the this photo is taken in between the experiment, where you can see that our photon has already started falling, and after some time I have captured it, where this is slowly you can see that the interference pattern becomes visible. And as I was telling you one thing, that there is something called EMCCT gain, which is given as 10 here. Corresponding to that, you can control actually the number of photons coming and falling, and with respect to h bar omega we can control the number of we can control the, by controlling the threshold actually we can control the h bar omega from the detector's end also. ND filters, first thing. Second thing is this EMCCT gain, and another thing is this exposure time of this EMCCT, with respect to which it depends upon that how fast we are detecting our like CCT plane, EMCCT plane is changing. Based on that it will of course change, because if I have a frame and after 1 second the second frame is coming, then number of photons in between are also integrated over that time, and we are getting the total number of photons. So if we are decreasing, so number of photons starts to decrease also. Here it is given as 0.02 second. You can understand this is very fast, but not so fast. Nowadays detector as nanosecond, picosecond based, picosecond level fast. So this is something 20 millisecond, and so the ND filter, exposure time, and EMCCT gain, three of these things are into the play to make it successful as a single photon experiment. And this is showing a particular frame, where you can see maybe you cannot, the visibility is not you cannot see because one photon has fallen over here and you cannot see that. And as we are accumulating over a long period of time and to check the interference pattern, so that's why you can see these over a longer time, like long exposure kind of thing, like of all long exposure with lots of frame accumulated over a certain time, whereas this is a particular frame. Now
Hello,
Yes,
Nilashi.
yes, yes.
I have a
Hmm.
question again.
Yes.
This is like kind of pattern we have received on PMT, है ना? Photo multiplier tube.
This is what we are using is
है ना?
EMCCD. Yes.
Yeah, so suppose I want to find out the source wavelength. Can
Hmm.
I find out this pattern to measure some?
Through this,
Can I? Can
through this pattern, you want to measure the wavelength, right?
yeah, source. Can
Yes,
I do it?
yes, yes. Yes, that's just the vice versa what we do in case of Young's double slit experiment in class 12 level or BSc level science, right? That experiment is there that you will get the interference pattern and after, from the interference information you need to trace it back the lambda of the source.
Okay.
Alright, so now this is a video of uh, this single photon experiment where it is showing that the photons are coming and falling on it. This is a particular frame, well, I mean single frame it is showing. If you see it very by giving it a very close look, then you can see that some brightness here, some photon is falling here, again here, uh, and 1 minute. Someone this one is excuse me, please can you please switch off your mute yourself, whoever has joined. Yes, so you can see that part frame there is sometime a photon is blinking up, and we are accumulating over all of the frames, and we to check that how the pattern is actually looking. And I have made this video very fast to convey it within just 2 minutes. It was actually a 1 hour experiment, and by taking one by one photons, we have accumulated all of the frames and we got the interference pattern. So just have a look that here there is one photon is blinking up, that means it is in a one frame, whereas this is the accumulation version of it. So let us wait to see that how it is changing, and you can see as well that I have made it very fast, this to such that it does not take much time, but it was actually a very slow experiment because one by one photon is coming, falling, and making the interference pattern. Now just wait and watch. So after some more time the pattern starts to, I mean it started to become visible that these streaks are coming, and single photons are coming, and after streaks starts to form. And now I am moving, I have moved this much more faster, this video, and we have reduced the ND filters. We have gain, now at this moment gain is same, but with the change of this gain and all of these things, and threshold value, you can see that previously just have a look. Previously the threshold value was set as 320, such that I mean by calculating the exposure time, MCCD, and all of those, we have an arbitrary value which we are calling as threshold value, which is 320. And you can see the photons coming over here are very slow. Now we are increasing it even more, which you will see 276 what 290, the number of photons starts become much more faster, 276, 275, and you can control it. It is a measurement based thing, because you know quantum mechanical experiments are very much measurement and detector dependent thing. And over the time, if you accumulate all of these frames like whatever we are doing here in case of this left hand side picture, then what we will get is nothing but this pattern, this fringe pattern, whatever we have also seen for this for this highlight level, like whatever we excuse me whatever we saw for this was much more smoother, because this was highlight level and lots of light was falling. Here it was one by one light was coming, and we see that we got some pattern here also, like this. So I hope now you understand that how we are telling it as a single photon interference and what is single photon interference. because lots of question was there regarding this. All right, and before going to the new problems, I would like to see. I would like to discuss about the first problem, the last problem of previous class, which I gave as homework. That you guys solve it. Uh, Homework is not so good word to use. Like just solve it, just to understand that whatever is shown to you, you can do that with some other field, and you can do it by yourself, because you need to do that for your assignments. So but all right, I hope many one of you must have done this, but let us solve this question also. So it is saying that consider a field Vt given by V a to the power minus I omega t plus b to the power minus I omega t b, where omega n and omega b are two frequencies and a, b are two real numbers. Find out the cross spectral density function of the field, find out the intensity of the field, find out the cross correlation function of the field. Is this field stationarity, at least in the wide sense, and find out the degree of coherence function of this field. This was very easy question, but that's why I gave you as homework, but let us solve it very first. So what was there is that what we can write, first let me write the function. What is given, Vt is given as a e to the power minus I omega t plus b to the power minus I omega bt. Question A, it is asking for cross spectral density function. So first let me calculate V omega, which is equal to, I hope everybody of you can see my iPad. Yes. So question is there in this slide, and writing is there in my iPad. If you want to zoom my iPad thing, or you're not visible, you can if my handwriting is not well, then you can tell me, and if it is well and you can understand, but like you need to zoom it, then zoom it by yourself. And
Visible, no problem, no issue.
okay, so V omega is equal to 1 by 2 pi minus infinity to infinity Vt Vt to the power I omega t dt. This is just the Fourier transform relation that we have already shown, and then if you calculate it, substitute it, then what will become? Minus infinity to infinity a to the power minus I omega t plus b to the power minus I omega bt, and here is e to the power I omega t dt, and equal to, if you do this, then it will become 1 by 2 pi minus infinity to infinity a to the power minus. I am writing all of these things very explicitly, such that everybody, whoever is here or sees afterwards, they can understand all of the steps. Omega b t, because all of the assignments are related to this type of questions only, and at least whatever is going at this moment, assignment a 1 2 3 4 1 2 3 at least, and you should be able to do those after seeing these solutions. So a delta omega minus omega a plus b delta omega minus omega b. I told you to revisit for some things, like revisit these things. One is Dirac delta function. Second is that spatial integrals, and very much important one among them, two integration are very important, that I have, or one I think I have already shown to you. If not, then I will show that which integrals are very important, and those you need to use for multiple cases, multiple problems. So just try to remember those. And thing is, in between the inside this we have this gamma function integration, which is very important. Okay. So these are the points, and now we need to, after getting this, we need to calculate the cross spectral density function, which is w omega 1 omega 2 v star omega 1 v omega 2, which is equal to v star omega 1 v omega 2. Why so? Because these are the direct, we can write it in terms of direct delta function. That means we have perfect correlation here. That's and that's why we can write this function as v star omega 1 v omega 2 and take it out from the ensemble average. Always be very cautious about the spatial concepts, some special mathematical concept that shown to you, like that time average, ensemble average, then ergodicity and spectral representations. These things always you should keep in mind. So based on that, I can now write the second term, that v star omega 1 v omega 2. Substitute those v omega, this thing, substitute this, and you will get a square delta omega 1 minus omega a, delta omega 2 minus omega a, plus v square delta omega 1 minus omega b, delta omega 2 minus omega b, plus a b delta omega 1 minus omega a, delta omega 2 minus omega b, a b delta omega 1 minus omega b, delta omega 2 minus omega a. So this is the cross spectral density function finally. So of course I have already solved these problems and make a note for myself to discuss in this class. So it is not like that I am doing spontaneously, but of course I these things, there are a lot of things such that I do not forget. That's why I make that, but you need to do it spontaneously in your examination. And main focus will be there in the solution also, because sometimes you may miss one of the very little calculation, and you can reach to a wrong solution. So be cautious for that thing. I just want to mention this because you need to take care of the speed also in case of examination. And when but these are the very standard rules they are following in case of this course, at least, which are, I have already told: Dirac delta, special integral, gamma function integration, Fourier transform, very important, Fourier transform. Because for doing quantum optics, for doing quantum optics, language, the mathematical language is very much important, and Fourier transform is one of the main mathematical language for this. And we'll use these four things very much there. Of course we'll also use one more thing you can note, that is green function you do not need, but the special functions like logger, Gaussian.
Excuse me, madam.
Yes.
We have find out cross spectral density of for W at frequency omega 1 omega 2. Can you explain what does the physical interpretation of this result output?
Okay. So yes, you can, of course you can. So this thing is that this first term is showing as omega, the basically there are two terms which corresponds to intensity, and two terms corresponds to cross correlation function. cross correlation sorry, we are talking about cross correlation function itself. Sorry, let me rewrite this. Okay, so here we are talking about cross correlation function itself. That's why we are finding out this delta omega 1 v omega 1 v omega 2 directly. Here if you find v omega v star here, whereas v omega 1 plus v omega 2, let me write, then I will tell. V omega 2 plus v omega 1 v omega 2 and its complex conjugate. Now complex conjugate means this let me write this also, let me write explicitly. V omega 1 omega 2. Now for the cross correlation function we are just calculating this thing. So this is just directly telling you the about the information of degree of coherence, where it is giving you at delta omega 1 a square delta omega, I mean there is some function of all right. Now if you do this now suppose you have some delta which is omega 1 equal to omega 2. If you if omega 1 becomes omega a and omega 2 becomes omega a, then what will happen? This will happen that only a square plus a square and nothing else. If you find omega 2 equal to omega b only, then it will be b square and nothing else. And if you write it in terms of omega a equal to omega 1 and omega b equal to omega 2 simultaneously, then it becomes a square plus b square plus 2ab. Okay, so that means it tells here it is a generalized form of omega a, omega b, omega 1, omega 2. In a particular case it can become perfectly it can become like no correlate not correlated with there is no correlation between two frequencies. In some case where there is just omega 2 equal to omega b, that means there is only one correlation in one point. And if omega a equal to omega 1 and omega b equal to omega 2, that means omega equal to omega b equal to omega 1 equal to omega b. That means all of the 4 points omega 1 omega 2 omega whatever the points are, mainly 2 points here, all of them are correlated. And if this is like these two, either of them are true, then it is like no correlation is present over there. So no coherence or correlation is present over there. So depending upon this omega 1 omega 2 and analysis of this w omega 1 omega 2, you can tell the information about the field itself. So field itself means in terms of coherence, degree of coherence. Like this is a coherent field, not coherent field, partial coherent field, how much coherent field can be found out if you have this v star omega v omega whole average. And if you find that v star omega v omega in at a particular delta, that means here again constructive destructive comes, where I can write it as max. And if v star omega v omega becomes mean, and if you sum this again and if you write it as plus, then you can by writing this you can even find that what is the degree of coherency there in this field. So you are finally, what is the conclusion is that you are provided with a field Now by calculating it and analyzing all of these with according to your condition, you can find out your degree, that what kind of field it is, and with this formula you can find out what is the amount of degree of coherence is present there in the field. Okay.
Okay, madam. Thank you.
So now we need to find out that what is the intensity. Intensity is given by IT, which is equal to V star T Vt. Again we can write it as a square plus b square plus 2ab cos omega a minus omega bt. If you just do this for this field, just do calculate and you will get this. And after that it is mentioned to calculate the temporal correlation function.
Madam, suppose I have to take average values for this a square plus b square plus 2ab cos. The answer would be a square plus b square. This would become.
Okay, so for that there comes the concept of absolutely random field, pure field. If it is absolutely random field, that means then it will become zero, because you are taking ensemble average and lots of different points or lots of different frequency which are completely random with each other. It will become zero. If it is not completely random, that means in terms of like classical thing, you can talk it in terms of randomness. And if you are talking in terms of quantum language, then you can talk about pure state, mixed state, or diagonal mixed state. So if you have a mixed state which is completely random, then of course this will become zero. If it is pure state, then you can write it, you can take the function out from the ensemble average and write that directly. So for that kind of case, you can this function will be present there. And as I have already mentioned, for this case we have correlation, like it is not neither completely random or neither we it is like we do not have no correlation. These are not such kind of case. This is a general case for which I am showing. For that this will be present there. But for a diagonal mixed state, or for a diagonal mixed state, this will not be present. Whatever you are saying, the average will go down, go off, it will go off.
Okay.
All right. So so the thing is that whatever I am currently solving, I have not given you any condition for pure state, mixed state, no information you have. What you have is a field. So just solve it in general way. When I will give this conditions, that if it is a pure state or mixed state or a diagonal mixed state, it is a random field or not random field, then you need to apply all of those things. Right now whatever we have not gone to that point that we are giving any condition. Right now we are solving it in general. And and again in terms of classical thing, this is not quantum, at this moment we are not discussing any quantum thing at all. But in classical mechanics, in classical level also, you need to, if we mention only that there is no correlation, then only you can use that. But here in this question no condition is given to you, so solve it for this general case. Do you get my point?
Yes. Yes.
Okay, so the temporal correlation function is given by tau t1 t2, which is equal to v star t1 v t2, and this will become a e to the power I omega a t1 plus b e to the power I omega b t1 into a e to the power minus I omega a t1 t2 plus b e to the power minus I omega b t2. Now calculate this thing, then it will become a square e to the power I omega a t1 minus t2 and plus b square e to the power I omega b t1 minus t2 plus ab I omega a t1 plus omega minus omega b t2 plus ab e to the power I omega b t1 minus I omega a t2. Excuse me. So find out the cross correlation function tau t1 t2. It is this will be like this only. And now the question is D, is this field stationary T, at least in the wide sense? See, now the thing is that what we called stationarity, that I have already introduced in the first class, that and for this that I am not going again. But since in this case intensity and temporal correlation function depends on the time of origin, because there is omega a t1 minus omega b t2, we cannot write this in just like t1 minus t2. So that's why it is very clear that this 2-point time temporal correlation function is not a function of delta t only or tau only, rather it is dependent on the origin of time. That means this field is not stationary. What was the condition for stationary? The condition for stationary was that intensity and 2-point correlation function and all of the other correlation functions should be independent of origin of time. And if it is wide sense stationarity, then it should, the intensity and temporal the correlation function, those two at least should be independent of origin of time. And here temporal correlation function is dependent on the origin of time, as we cannot write every terms in terms of delta t. So this is not stationary. Now last but not the least, of course we have several things to do, but this question E is find out the degree of coherence function of the field. That means gamma t1 t2 equal to capital gamma t1 t2 by root over of capital gamma t1, that means it1, and capital gamma t2, that again means it2 only. Anything you can write. That means again it will become v star t1 v t2 v star t1 v t1 v star t2 v t2. Of course ensemble average are there, but here we can write as it is we can write it in terms of time average, and here as it is fully correlated field, so we can directly take it out from the average and write it. So what it will become? It will become 1. Okay. So this was our question, and there are several questions related to these in your assignments actually. All right, so this now I have already discussed about Young's double slit experiment or Young's interferometer, and I was talking about this Wolf equation at the end, when we start discussing about the double slit experiment and single photon experiment. So let us come back again at this Van-Cittert-Zernike theorem, which I was mentioning. Wait a minute. So this is the Van-Cittert-Zernike theorem, where it is showing there is some source and R1, it is propagating, and of course we know when it propagates through a spherical wave, which can be considered as summation of multiple of plane waves. And if you propagate through to some R1 and R2 distance, then Van-Cittert-Zernike theorem gives us some weird behavior, which is actually true in the nature. Now the thing is that what happened, what did we do? We did that we have studied the coherence function and coherence properties in one way in this spatial degree of freedom, where we studied the correlation function to understand the nature of the field, and we studied the how to do the Fourier transform and find out the cross spectral density in spatial degree of freedom as well. Now for the temporal coherence function, temporal coherence in the temporal degree of freedom, we found that the coherence properties are decided by how different field vibrations are correlated in their frequencies. And those we saw that there is something called Wiener-Kirchheim theorem, through which this that capital gamma or capital tau, this capital gamma r1 r2 t1 t2 is just a Fourier transform of cross spectral density, which is w r1 r2 omega 1 omega 2, and vice versa, which is called as Wiener-Kirchheim theorem. Similarly, the coherence properties between two spatial positions are decided by how the field vibration are correlated in their spatial frequencies, and correspondingly we got the similar analogy for getting the Wiener-Kirchheim theorem in the spatial degree of freedom. We also derived that the propagation of coherence can be studied through Wolff equation, which are in the form of differential equation. Now what we need to do is that we are studying the propagation of coherence through an integral equation for a primary source, which is shown with O. So we'll look here how the spatial coherence properties of the field emanating from a primary source propagates to a far field. So for that what we did is we have solved the Helmholtz equation, and you know that by using the green function and all of this we get the solution in spherical coordinate as kr by r, like something like this from Helmholtz equation. Now after considering an infinitesimal area element where we are measuring it, and we integrate over that total area over this entire source, and then what we get is V r1 omega and V r2 omega. Let me maybe write it once, although it was described there in the lecture, but just to give you a glimpse that what was done there. So suppose see the picture is that O is there, source is there, it is propagating, and what we have after propagating some distance, this is r1 and this is r2. Now if we solve all of these equations, there are lots of equations, then what we will get is that V r1 omega equal to V r1 dash omega e to the power I k r1 by r1 lambda 1 k d2 r1 dash, and similarly for V r2 omega. Now if you find that V star r1 omega V r2 omega, then what you will get is the field correlation itself, which is nothing but this W r1 r2 omega r1 r2 omega. Now so we have something W, which is now a propagating solution, which is coming from the Wolff equation by solving the Wolff equation, by solving the Helmholtz equation, and if you calculate all of these things, whichever you all these things were actually described in your lecture in very well manner, then finally what you reach to the solution is for W and for tau, how they are propagating, and that is what is told by Van-Cittert-Zernike theorem. And this was finally W R1 R2 omega equal to k by 2 pi square, where k is the wave vector and this is the A, which is integrated over A means area of the source, and R1 dash omega e to the power I k R2 minus R1 by R1 R2 D2 R1 dash, and you can see what are R1 R2 R1 dash R2 dash R1 R2 everything in the picture. And let me write, R1 can be written in terms of like this, and similarly R2 can be written in terms of this for far field. And if this is nothing but you can understand that propagation of spherical wave solution by using what we get generally, like e to the power I k r by r type of forms. And as we have correlation, so for one you have e to the power I k r by r, for another one you have e to the power I k r by r, and that is that becomes e to the power I k r minus r2 by r1 r2. So nothing but you can remember it in this simple manner. So this is the thing that Van-Cittert-Zernike theorem tells mathematically. But very importantly, what we understand by here, like we have a source, let me maybe give it in red color. This is a source which is a finite enough source, and lights are coming from there which are incoherent. If you measure something here, it is incoherent, or you can produce partial coherent. But now suppose these are propagating for a far field. This is propagating. Now you have a previously we have a detector here. Now we have a detector here. We have a detector here, or here, or anyone, such that we are the source is in the very far field, and we are detecting at very far field. Then what, now the behavior of source becomes is nothing but a coherent field. So this says Van-Cittert-Zernike theorem in short form it is called as VCZ, that after propagation of incoherent or partial coherent source, it becomes coherent. So this is very weird, which I found very weird. I don't know if you feel so or not, but this is weird, but this is the truth. Now and always, mostly whenever we are doing experiment, source is somewhere, we always take after propagating to some distance only we are measuring anything, even with respect to a source which has a 0.5 millimeter of beam waste for a natural laser light source. If you are taking a measurement anything after 10 centimeter also, then 10 centimeter is larger than 0.5 millimeter. So for although laser is not a good example because laser is itself a coherent source, a perfect coherent source, but for led or anything else, you can, if you do such, if you propagate the thing and measure with the detector, then the degree of coherency at that point start to decrease because of this Van-Cittert-Zernike property or this theorem. So this is one of the thing, and mostly whenever we are working, we consider Van-Cittert-Zernike theorem as if you are at a far distance from the source. And this is also actually used very much in case of astronomy. So okay, so after this, let me let us solve another problem after. So this problem is also very I hope a heavy, this is also a heavy problem. So let us start first reading this. This is a, there is a source, it is coming and it is splitting through the beam splitter, going to this mirror 1 and going to this mirror 2, and this is a detector, and you can understand this is a Michelson interferometer. And beam splitter, here it is mentioned BS stands for beam splitter, M1 is a mirror 1, M2 is a mirror 2, RBS and RTBS are the reflection and transmission coefficient of the beam splitter, while RM1 and RM2 present the reflection coefficient of two mirrors. These are the given to you. Now the time taken by the light from source to the detector through the two interferometric arms are given by T1 and T2. Okay, now suppose now this is telling problem question A. Suppose the electric field of the source is given by this est equal to E0 to the power minus I omega t, where E0 is real and omega is the frequency. Calculate the intensity at the detector as a function of t and also visibility. Consider RBS and TBS equal to 1 by root 2. That means this is a 50-50 beam splitter, and RM1 and RM2 equal to 1. Alright, so let us start the solution, start the problem.
Both the mirror is fixed or one of the movable?
No, right now, of course, for the Michelson interferometer, you need to add some this is not moving. These are fixed, but already it is told that one path is taking T1 time and one path is taking T2 time. That means they have some path difference, which is introducing path difference itself.
Good.
So let me solve this problem. So at the detector plane ET, if we write it as ET, then it will become R beam splitter RBS, that is a reflection of the beam splitter, and RM1, that is a reflection from the mirror 1. First we are considering for the first path, M1 path, T1 path, and it can be also like RBS is the reflection coefficient of the beam splitter. It is reflecting, going through this. Again, when it is coming back, then what will have? It will have transmission, not reflection. That means it will have TBS. And when it will go to the second path, and of course that means here is one reflection, first reflection for that RBS. Here it is one reflection from the mirror, that's why it is coming back to here, that means one RM1. Again it is transmitting to the beam splitter, that means TBS. Now we have it is going through this source, passing through this beam splitter and transmitting, that means one TBS. Then one reflection from this mirror, that means RM2, and again it is another reflection from the beam splitter, that means RBS. So all of these things for the different path need to be considered, and after considering all of this, we can write we can write RBS RM1 TBS into ES T minus T1 for the first arm, because one reflection beam splitter, one reflection mirror, one transmission through beam splitter, first path, plus TBS RM2 RBS ES T minus T2 for the second path. Now it becomes E0 by 2 to the power minus omega T minus T1 plus e to the power minus I omega T minus T2. Why? Because it is told to you that RBS equal to 1 by root 2, TBS equal to 1 by root 2, and RM1 and RM2 are 1 1. So RBS TBS 1 by root 2, 1 by root 2, so 2, E0 is already there, RM1 is 1. Similarly, RBS TBS 1 by root 2, 1 by root 2, 1 by 2, and RM2 is 1. So this is the electric field at detector. So the intensity becomes at the detector something like IT E star TET, which is E0 star E0 2 2, I mean 2 2 2 into 2, that means 4, we can write directly. T I omega T minus T1 plus E minus I omega T minus T2 star E minus I omega T minus T1 plus E minus I omega T minus T2. This will be equal to E0 square by 4. If you do this, this is the star is there, that means it will become plus, and this will become minus, so it will become ultimately 1 1, and the 2 cos the cross correlation term will be presented there, and it will become 2 cos omega T2 minus T1, that is E0 square by 4 1 plus cos omega T2 minus T1, because 2 is taken 2 is taken common, that means it becomes E0 square by 2. And so the question was to calculate the intensity at the detector as a function of t. Yes, t means here tt gone, so it is become t2 minus t1, that means actually the function of time. This first thing we got, and second thing it is told that calculate the visibility. Which will become V equal to I max minus I min this thing, I max minus I min by I max plus I min, which will become nothing but, if you substitute them, then it will become I max minus I min, it will become 1. Calculate it. I max means that this omega T2 minus T1, this phase will become 0, such that cos 0 means 1, so it becomes 2. Mean become cos 0 means 1, so 1 plus 1 2, and if it I means this will become pi, that means it becomes 0, that means 1, and here 2 uh, 2 minus 1 or 2 or 2 plus 1, 2 plus not 1. Here it will become I mean is
I
1.
minimum, I minimum, you will get 0 because cos pi minus 1 plus 1 cancel out
Yes, yes,
from
yes,
equation. Yeah.
yes. Prasant, can you tell me once what you are telling?
If you see equation 1 plus cos omega t2 minus t1,
Hmm.
this should be for cos pi. Cos
Hmm.
pi minus 1,
Hmm.
so 1 cancel 0. So I minimum will be get 0.
Yes, 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 yes.
So 2
Thank you,
by 2
thank you,
equal
thank
to.
you. Yes, yes, yes. Correct. So it becomes 1. Actually, cos pi equal to minus 1. All right. Thank you, Prasant. So yes, so it will become 1. So visibility 1 means we have perfect interference with perfect coherent light. So if you do this set up this kind of Michelson interferometer, then what you will get a interference fringe with visibility of 100% or visibility equal to 1. So the next question becomes, so the next question it is telling is, suppose the electric field of the source is given by this, where E0 is real and omega is frequency, and calculate the intensity at the detector as a function of t, where t and also the visibility where RBS, TBS are changed now. Previously it was 1 by root 2, 1 by root 2, now it is nothing but 0 0.8, 0 0.6. So I hope everybody has already understood what you need to do, but still let me do this. Is becomes et like we got this et. Let me copy this. We have this field, we had this field. It is a general case for which we have written. For 1 by root 2, 1 by root 2 we have substituted that, and now for 0 0.8, 0 0.6 we'll just substitute this. So what we'll get, 0 0.8 cross 1 cross 0 0.6 is 0 e to the power minus I omega t minus t1, and 0 0.8, sorry, 0 0.6 cross 1, 0 0.8 is 0 e to the power minus I omega t minus t2. Finally it will become 0 0.48 e 0 e to the power minus I omega t minus t1 plus e to the power minus I omega t minus t2, and the intensity will become 0.48 square. I am directly writing. I already solved this previously by myself before this class, so you guys just please solve t2 minus t1. So this is the intensity, and if you find the visibility, then it will become 1 again. So these are the answers. So so for the this was a so by this manner you have already understood how to do it for Michelson interferometer through this question. So you have learned from the Mach-Zehnder interferometer, you have also learned for the Michelson interferometer, and similarly, if you understood that how we are doing solving all of this, then you can do it for any interferometer now. But we have some more question regarding to this, and I hope these are some of them can be there in your assignment or your quiz, or maybe in your end sem mid sem. So so question C is telling, suppose the electric field of the source is given by this, where E0 is real, omega and omega is frequency. Calculate the intensity detector function visibility. This, oh, see, we have calculated. No. So what is
Nakshi question is not visible.
question? It's not visible. Okay. Is it visible? Can you see it? Hello?
Not visible, madam.
Okay.
Not visible.
All right. Let me stop here and do it again.
Yes, this is visible right now. Yes.
Okay. Okay. Now you can see, right? 1 minute. Let me share my writing screen once. Okay, so the question is this, and the answer I'm going to write. So the question, it is telling, suppose the electric field is this, where E0 is real, omega is frequency. Calculate the intensity at the detector and visibility, where RBS TBS equal to 1 by root 2, RMN equal to 1, and RM2 equal to 0.8. So do I need to solve this again, or you have already understood that what you need to do? You have understood, I think.
Yes, we can do it. No problem.
Yes. So this is the C and D are same, just like different things. No matter to do, no need to do so many times. Let us C and D similar. Similar things are provided here, because if you can understand that maybe what we are doing here at the discussion just slightly change, and you can get it in the assignment or quiz or mid sem or end sem. Okay, now the E. Suppose the electric field of the source consists of two separate but completely uncorrelated frequencies. Now what Prashant was telling, that the conditions are started to given, like previously whatever we are doing, still now whatever we are doing, those are for general case, that's why we are doing all of the things. Now the starts to give the conditions. So finally we have reached to that point where it is saying that completely uncorrelated frequencies between omega and omega A and omega B, such that est e to the power minus I omega at, even electric field is also given to you. So it depends highly on your research, I mean your problem goal, what it is provided to you, you will just do the same. And where and here it is also told that ea and eb are random variables, with ea star ea equal to eb star eb equal to I0, and ea star eb equal to 0. This is what I was telling before, some time before, right? So now calculate the intensity as a function of t, where RBS TBS are 1 by root 2, RM1 equal to RM2 equal to 1. So for that, what do you need to do is to do this just calculate whatever it is given to you. The same thing you need to do, nothing extra, nothing is different than the previous thing, just you need to calculate it. All of the information is given to you, just find out, write the electric field at the detector and find the intensity at the detector, which you can calculate just like the previous thing. So do I need to calculate it again? I don't think so. So the similar thing, like A, B, C, D, E, all of them were similar, just different RBS, TBS, RM1, RM2, and different condition. So do this C, D, E by yourself to practice it more. Now finally we have reached to this problem 3. 1 minute. Problem 3, because you have already reached to quiz or assignment 3, so where it will be helpful for doing this kind of problem with the spatial correlation. Now till now we were doing all the things by taking the help of temporal. Now this is the first problem where you are seeing in spatial degree of freedom. So problem 3, it is telling explain qualitatively the statement of the Van-Cittert-Zernike theorem. So let me hear what we can say. I have already written, but still, the Van-Cittert-Zernike theorem quantifies the propagation of spatial coherence with distance for a spatially extended incoherent source, where it states that the effective coherence area of such an incoherent source increases with the propagation distance. And this can be understood by observing that an incoherent source tends to behave as a point source as the distance become very large. That means an incoherent source becomes spatially perfectly coherent source at a very large distance. This is what it tells. So the next question, it is saying, starting from the Helmholtz equation for ux, yz and this equation, obtain the paraxial Helmholtz equation. This is this is shown to you in your lectures, that how to do it, and then it is saying that for ux, yz in situation in which it can be represented like this, write down all the approximation involved, like paraxial approximation, far field approximation, r whatever it is taken. All of these things were mentioned to you in the lectures. I have not gone through all of these in today's class, so I hope this is this part from lecture. This question I have just given to make you remember that although it will not be there in MCQ based question, but these things you need to do it by yourself, at least one by with your hand. So that's why only. So just see the lecture. If you have any question, you can drop me a mail or comment in the YouTube chat section, or use the ask a question portal. Now the second thing, the problem C, it is telling, prove that the cross spectral density is Hermitian. This is very interesting. Like, can anybody do that? Hmm? So first thing what we knew is that what we didn't focus, but right now we are focusing, is that cross spectral density function is a Hermitian. And let me do the proof very quickly, and this is very sweet, not very difficult, very
Madam, one thing I
yes.
want to ask one question. The cross spectral density function is Hermitian. What does mean here?
Hermitian means that if you have row 1 and row 2, 2 points, right? So Hermitian means can we consider, if we consider row 2 as row 1 now and row 1 as row 2 now, then will it be same or not? And intuitively we can understand it does not matter. This is our consideration, that what is r1 and r2 we are considering. So it is irrespective of our choice, that what we are considering it. Whatever we, if we want to just check the correlation between 2 points, whoever is whatever, if it is correlated, then it will be correlated. That's what Hermitian tells here. Okay, so what you need to show is that W star rho 1 rho 2 omega equal to W rho 2 rho 1 omega. Now did you understand? Did you understand, Prasad?
Okay, madam. What does I understand? I think Hermitian means, I think, is related to energy for Schrodinger wave equation. Is it
Okay,
same
okay.
or different?
So the thing, or that energy is Hamiltonian, not Hermitian.
Okay, I have to read it. I don't know right now.
Yes. So it is very good that you are thinking these things and you are having doubt. So very nice. So when you will come to Hamiltonian, then you will see that energies correspond to Hamiltonian. Hermitian means, can we revert it and get the same thing, kind of thing. Or
Okay.
this is if this is and by intuitively you can understand if rho 1 becomes rho 2 or rho 2 becomes rho 1, this is our choice. It does not, it should not affect the source or field, right? So intuitively even we can understand that this should be a Hermitian field, that it is reversible kind of thing. So v star rho 1 omega, v rho 2 omega, it will become now we can write it in terms of the whole star of it, that means v rho 1 omega, as I have taken the w star omega rho 1 rho 2 omega. Now it becomes v rho 1 omega, v star rho 2 omega, and it will become v star rho 2 omega, v rho 1 omega equal to w rho 2 rho 1 omega. That means it is our choice, so it is Hermitian only. And Hermitian and Hamiltonian are different things. Hamiltonian is total energy, there is nothing to do, they are not similar, Hermitian and Hamiltonian. And last but not the least, this D, we will not solve problem 4 maybe today, we will discuss start discussion problem 4 from the next week. So the problem D, it is saying that the Wolf equation for the cross spectral function is given is as this. You know the Wolf equation. Now derive the Wolf equation for the cross spectral density function. So cross correlation function is given to you. Now you just need to do it for the cross correlation is given to you, and you need to do it for the cross spectral density. Just nothing but the Fourier transform. So if it can be written in terms of just for like 1 field 1 delta 1 squared tau r1 r2 tau equal to 1 by c squared del 2 delta tau 2 tau r1 r2 tau. Then for the cross spectral density, what you can write? You can just write nothing but the Helmholtz equation, because we know this is the wave equation, and in the Fourier transform basis of this, it should give you the Helmholtz equation. I mean Helmholtz equation of cross correlation, that means Wolf equation. Correlation, that is Wolf equation. This is the wave equation for correlation, that is Wolf equation in the position basis, I mean in one basis, and this is just the conjugate basis. And if you want to solve it, then focus on, and then let's see it. Then suppose we have tau 1 square tau. This is just by intuitive manner I have written. You guys can also think that how I have written directly. But if you want to solve it and check it, then this is the mathematical perfect method how we can reach to that. And whatever we can do it for delta 1 square, we can similarly do it for delta 2. Zero to infinity e to the power minus I omega tau d omega. Then I am taking the integration in both hand side. Now we can write it like the first thing is similar, nothing new, and this part will become, if you do the derivation, it will become del 2 delta tau 2 minus I omega tau d omega, then minus omega square by c square, 0 to infinity w r1 r2 omega to the power minus I omega tau d omega. So finally it will become integration 0 to infinity delta 1 square w r1 r2 omega plus omega square by c square w r1 r2 omega e to the power minus I omega tau d omega, which is equal to 0. That means it will become del 1 square w r1 r2 omega plus omega square by omega by c means k, so k square w r1 r2 omega equal to 0. That means what I have written here, we have reached to there. The similar thing, this is intuitively and this is proper solving it by solution, by solving it like properly. So this is the thing. All right, so the problem 4 is given as you can try it at home. All of the things are already there in your lecture. You can try it by yourself, but from the next in next week I will discuss and solve this question. So it is just the similar thing whatever we are doing in case of temporal degree of freedom, these are from for spatial degree of freedom now. So you can give it a try. I will not discuss today. So so let me today stop our discussion, but before that maybe I would like to mention the thing that today we have discussed the single slit experiment, single photon interference experiment, as well as the double slit experiment has shown all of these things. So whoever has joined lately and and if somebody has missed, then please go through these ones. And finally we learned about second order spatial coherence theory, some essential mathematical concepts of it, quantifying the spatial correlation, Wolf equation, Van-Cittert-Zernike theorem, all of the things that we solved 5-6 questions problems. You can do some you can do the problem which I gave the last one. And we also, most importantly, we have shown you the experimental setup and discussed the double slit experiment as well as single photon double slit experiment with a single photon. So and again for anything like if you have I have already shared with you the drive folder link. Please visit drive folder to get all of these materials. And somebody asked me for some book also. So book I generally do not upload, but if you need any book from me for reference, you can ask me. I have the books, I can provide you, but for the the privacy policy and all of this ownership policy, I do not upload this for in this drive thing. If you need, I can share it with you, or you can also find it by yourself. And I have also given the YouTube link of my channel, or my name, you can search and find it in the YouTube, or you can you have already the playlist in your through the SWAM portal. So you can check always all of these things, and you can reach to me via my mail, which is this. Let me write. And you can also write in the YouTube chat section. And last but not the least, ask a question portal.
And then actually,
Yes.
suppose I have an official mail. Can you share the book? There's no issue.
Yes,
Electronic
yes,
book.
yes. You can, if you mail me by asking it, I can share with you.
Okay.
Okay. All right. So let us call it a day. If do you have any other thing to ask?
Madam, again share your email ID, please.
Yes, I have just written in the chat box. Can you see it?
Chat box. I think. Please send again.
Okay, I'll send it again. Did you get it?
Yes, yes.
All right. So this is my chat. This is my sorry. This is my mail ID. You can contact me there also. All right, so let's call it a day. This is our week 3 discussion, and let's meet all of with you on week 4 and Saturday, next Saturday, 5 to 7 p.m. All right, bye.
Bye. Thank you.
Thank you so much.